Hey everyone, welcome to BCP Med. In this video, we're going to be looking at the periodic trend of effective nuclear charge using the simplest approximation for the value, which uses just the number of core and valence electrons. Let's go ahead and get started. First and foremost, what is nuclear charge? Well, if we look at these three nuclei for hydrogen, helium, and lithium, we can see that they contain 1, 2, or 3 positively charged protons respectively. The number of protons makes the element unique. Each proton contributes one full positive elementary charge to the atom, and so the total nuclear charge is just going to be the number of protons, or the atomic number. It is always going to be a whole positive integer. We all know that the nucleus pulls on the electron cloud, but how much each electron feels the nuclear pull actually depends on where it is. This is because the core electrons, those one energy level or more below the valence electrons, actually block or shield some of the nuclear charge from the further valence electrons. You can imagine it sort of looking something like this. Each blue arrow represents the pull of a single proton onto the valence electrons, whereas the red arrows represent the repulsion caused by a core electron. Remember, electrons repel one another because they are like charge. Because the core electrons are much closer to the nucleus than the valence electrons and carry an equal and opposite charge to the protons, from the point of view of the valence electrons, it looks almost as if one proton and one electron combine to negate one another to form a neutral charge or to eliminate the charge of a single proton. So the effective nuclear charge that those valence electrons feel is reduced compared to the actual nuclear charge. And so we often represent the effective nuclear charge, Z effective, as Z, the nuclear charge, minus the shielding constant, S, which is related to the number of core electrons. And we'll talk more about how exactly you calculate that in the next slide. Because valence electrons only feel this Z effective, or this portion of the total nuclear charge, atoms do not continue to shrink as the atomic number increases. If the nucleus exerted its full pull on every single electron, as for every proton that was added, each electron would feel a stronger attraction, and eventually the atoms would just get smaller and smaller and smaller and collapse into the nucleus. Now, in reality, the way in which the core electrons cancel out the protons is not really easy to determine. And so determining the true effective nuclear charge is going to be kind of different. However, what we're going to do is we're going to assume that the core electrons each cancel out the attraction of one proton to simplify our lives a little bit. Now, the way that we're going to do that mathematically here is with our simple little shielding equation. What we're going to do is we're going to approximate S, the shielding constant, as just being equal to the number of core electrons. Right? So we're going to approximate S as equal to the number of core electrons. In our approximation, the repulsion onto the valence electrons caused by a core electron is going to exactly cancel out one proton worth of nuclear charge. Now, how do we know the number of core electrons? Well, it turns out that's just going to be equal to the number of total electrons, aka the atomic number Z, since atoms are neutrally charged, minus the number of valence electrons, which you can easily find from the group number. With a little bit of arithmetic, and I encourage you to do this by hand, you will see that if you replace the shielding constant S with Z minus valence electrons from our core electron expression here, you'll get that for a neutral atom, Z effective is actually going to equal or be approximated by the number of valence electrons. This final simplification only works with non-transitional, so non-transitional metal, neutral atoms. You cannot do this with ions. With ions, you have to actually count the number of core electrons. But let's go ahead and look at an example. Let's start with fluorine. Fluorine has the Bohr model shown left, which we would observe has 9 protons, 2 core electrons, and 7 valence electrons. Using our equation, we could say either of the following. We could say, well, Z effective is going to be the nuclear charge, which is 9 protons, minus the number of core electrons, which we can clearly see from the Bohr diagram is 2. So that's going to give us a Z effective of 7. On the other hand, we could actually, let me wait a second on the nitrogen. On the other hand, we could go ahead and just say, well, how many valence electrons does fluorine have? It has 7, which is indeed the effective nuclear charge that we got from the mathematical equation. Now, we can do the same with nitrogen. We know that nitrogen is going to be group 15, so let's apply our valence electron trick. Group 15 elements have 5 valence electrons, right? Group 15, 5 valence electrons. That means nitrogen is going to have an effective nuclear charge of 5, right? Now, based on our simple little approximation here, we can construct a nice periodic table trend for the Z effective. And as you'll see, it'll line up very nicely with the number of valence electrons as well. The Z effective increases going towards the right-hand side of the periodic table, reaching a maximum value of +8 for the noble gases, except for helium, which is +2 because it only has 2 protons. It has a low value of +1 for the alkali metals. Notice that with our approximation, the effective nuclear charge is equal going down a column. And this is actually evidence for the fact that elements in the same group or the same column are going to have very similar chemical properties. Now, I hinted at this a little bit earlier, but I want to discuss how you find the Z effective of an ion using our approximation. And we're going to go ahead and start with anions. And the reason that you need to do this is because the number of valence electrons has changed when you create an ion, so it's not just going to equal the effective nuclear charge now. So if we start with an anion, let's go ahead and start with the neutral atom of fluorine. We know that fluorine has an effective nuclear charge of +7 from our earlier calculation. If it were to ionize by picking up an electron, it would become the fluoride anion, which is F-, which is now going to have 2 core electrons and 8 valence electrons. So to find the effective nuclear charge, we're going to do it the exact same way we did with the mathematical expression. We're going to say, well, Z effective is equal to the nuclear charge, which is 9, minus the 2 core electrons. And it turns out that for fluoride anion, the effective nuclear charge is still +7. This happens because unless we add enough electrons to add a whole new energy level, which never really happens, the number of core electrons is always going to remain the same. We're only adding to the valence level, and we don't care about valence electrons. So, anions are always going to have the same effective nuclear charge as the neutral atom, right? Z effective does not change for anions. However, because there is now more electrons present, there's going to be more repulsions. And so with the same Z effective, the ionic radius is going to increase compared to the atomic radius. More repulsions with the same amount of attraction. If we go ahead and turn our attention to cations, we're going to see something very different. If we start with beryllium, which has 2 core electrons and 2 valence electrons, we would calculate that it has a Z effective of +2. When we strip 1 valence electron, we can see that the Z effective stays the same just as it did for the anion because we only affected the valence electrons. However, something really weird happens when we strip a second electron. Right? So Z effective for the 1 electron removal is still +2, but when we strip a second electron, we completely remove the whole valence level and things start to get crazy. So by removing the original valence level, we have redefined what the core and valence electrons are. The energy level below the original valence is now the valence level. So this is going to cause Z effective to increase because the number of core electrons has decreased. We turned some core electrons into valence electrons. As in the case of beryllium, there are no more core electrons, and so the full nuclear charge of +4 is going to be felt. This effectively increases the effective nuclear charge of the atom from +2 to +4. And this large increase is part of the reason that you do not continue ionizing the cation. You stop once you remove the whole valence level because the effective nuclear charge shoots up the moment you get rid of the original valence level, right? So just to summarize, Z effective increases for cations once the full valence is removed, and this is what prevents further ionization of any core electrons under normal conditions. So to close up here, I want to go over some of the consequences of effective nuclear charge. It turns out effective nuclear charge plays a huge role in determining chemical reactivity. How easily electrons are removed from the nucleus depends on how tightly they are held, i.e. the nuclear charge, since the electric force is based on charge and distance. A smaller Z effective means that an electron is going to be held more loosely and it will be easier to remove, which means that that element with the lower effective nuclear charge is going to have more metallic character and a lower ionization energy. We can visualize that with this picture here, as the yellow arrow represents the energy being inputted to remove an electron. The smaller the effective nuclear charge, the less energy is needed to kick off that electron. Conversely, how easily electrons are added to the nucleus, or to the atom rather, is correlated with a high effective nuclear charge, a high Z effective. The higher Z effective is, the easier an atom can pull in another electron and hold on to it, meaning that the nonmetal character is going to be greater for those elements, and that the electron affinity and the electronegativity of those elements is also going to be higher, right? We can visualize that here as well. If we imagine the nucleus is pulling in that electron, it's capturing an electron, the larger the charge of the nucleus, or rather the larger the effective nuclear charge at the valence distance, the easier it is going to be to pick up that electron, since the electric force being exerted is again proportional to that charge. Right? So to summarize, effective nuclear charge is a huge determinant in chemical reactivity, and specifically it's going to impact three other periodic trends: ionization energy, electron affinity, and electronegativity, which correlate with metallic and non-metallic character. And with that, we've actually gone ahead and reached the end of the content for this video. Thank you guys so much for watching, and if you enjoy what you saw, please like and subscribe to the channel. Make sure to check out our other videos on the chemistry playlist to learn more, and if you're looking to branch out, check out our other science playlists. See you next time!